try to apply the basis theorem of linear algebra of those vectors to those functions as generalized as infinite dimensional vector. So what is the basis theorem? It says that suppose that you have an n-dimensional vector space. So it's defined by vectors that, well, they have 10 they have n components. And the basis theorem says that if you can find a set of vectors bi such that if you can find a set of vector bi where I ranges from 0 to n minus 1, which means that there are n such vectors. If you can find such a basis, so if you can find a basis of n such vectors such that the inner product of two elements of that set is given by this equation where dii equals 1 and dij equals 0 if I is not equal to g. If you can find such a set, then any vector, can be written as each of these numbers are inner products. So they are numbers. So this theorem essentially say that you can decompose each vector as a sum of those basis elements. The basis elements have to satisfy this equation, such that if you take a same basis element inner product with itself, it's normalized. And if suppose that B3 times the inner product with two different basis vector is 0, if it satisfies that for any combination, then you can decompose that vector as a sum of those basis vector. Now let's apply that to those functions that could be said that could be made equivalent to vectors with an infinite number of dimensions, with epsilon tending to 0, as we defined earlier. So I cannot prove it to you guys, but suppose that we have the faith that this theorem holds as the number of dimension increases and epsilon goes to 0. We try to believe, because I cannot prove it, but there is a proof out there, that if the vector extracted is extracted with a number of dimension that tends to infinity, so that epsilon, which is equal to 100 divided by n, tends to 0, we want that property to hold. So suppose that it holds, then let's find some vectors, a set of vectors, such that when you take the inner product from 0 to 100, it gives this, the Kronecker delta. Then by fifth, we would want, and we would want also that those vectors are finite, so that you can see that it can be put in correspondence with a finite vector, because all finite vectors generally, well, all finite vector has finite inner product, has finite length. This is it's kind of like a length squared. So if we can find a set of bases, we know that when epsilon is finite, when epsilon is larger than 0, we know that this formula has a theorem attached to it, because when epsilon is larger than 0, n is finite. So we know that it applies, but as epsilon gets closer to 0 and increases towards infinity, we still want to believe that it applies to those vectors that we defined, that we extracted with infinite dimensions. So if we believe that, then we will have to believe that fx is given. So remember when I said that each dimension of the vector is given by f, say 0, square root of epsilon, and so but as epsilon tends to 0, we will say that this function can be represented by fx square root of epsilon. And so if we want the theorem to apply, then we would want that this here is given by, we will want then that the components of this infinite dimensional vector will be such that it's equal to sorry, I wrote in the wrong given by, these are the components such that the inner product of the basis elements, the basis vectors, is given by Kronecker delta as I defined earlier. If we can find those basis elements, then the theorem, if we believe that it holds also in that limit, the theorem says that So written out algebraically, it would mean that sorry, once again let's call that J for now. As epsilon tends to 0, this equation will be given by so let's say m the dx. This is just it's just epsilon as epsilon tends to 0. So written out in a more functional way, in a more in the way that we describe it in the present, is given by for each component. So here you have it. So you have the decomposition. This is inner product. And this is the formula for decomposing a function in Hilbert space. And you will see that as I increases, like as you take a sum here, from I to equals I equals K, and as K increases, this part here will get closer and closer to fx, which in vector language, this is just a component at x equals I dx, or I epsilon. I do not know if it also works for complex to complex, but I feel like that it should work also. But then the integration, suppose that you have a like if you take the inner product in complex I feel like I'm not sure if it applies. No, I'm not really sure. But yeah, in general, when you have functions from the real number to the complex number, the inner product will be defined in that way. where this is simply, suppose that fx equals ux plus vx, then the complex conjugate of that function is, and you will find that in that case you will have that fx is equal to where bi